So at this point, when you're talking about exponential equations, we can really start to look at some of the applications of exponential growth, and one of those is a population model. Okay, there's actually a pretty fascinating book by the author. Well, it's fiction. It's pretty good. It's called Inferno. It's by Dan Brown. Um, it's quite an interesting read. I won't ruin the ending for you, but it's got a pretty good twist to it. It's a long book, but if you like reading fiction, check it out. It talks about populations and such. Anyway, not to get too far off topic, but at this point, we've probably discussed the what we call the Pert formula. Okay, and the Pert formula is a formula of exponential growth. Okay, where each one of these variables represents something specific, right? Keep in mind that E is not a variable, right? E is what we call the natural base, right? The reason it's called the natural base is because for some naturally occurring exponential growth and decay models, E is a popular choice to show that, right? So we're talking about population growth like so, okay, which can be modeled with functions like such. So A is the amount, right, after some period of growth. P usually stands for the principal amount or the original amount, right? R is the rate of change or the growth, what we call the growth rate, okay? And then T is a unit of time, typically in years. So they're giving us this formula here, okay? And if we use this formula that says, this formula models the population of a US state A in millions, T years after 2000. So this number is number of years after 2000. That's what T represents. So what was the population of the state in 2000? Well, the year 2000 is 0 years after the year 2000. Okay, so we're really saying A equals 15.7 e to the 0.0416 times 0, which if we find the product of this exponent, we get 0. And if we follow the order of operations, e to the 0 power is 1. So we get 15.7 million, right? Now, you wouldn't have had to do that if you understood what the variables in this formula stand for. We said P is the principal amount, which is the beginning value. So 15. So if there's ever a coefficient to your exponential term, this number is the original population or the original amount. Okay. E, that's our growth factor, and this is our growth rate, and T is a unit of time. When will the population of the state reach 18.7 million? When is a question talking about time, right? So for part B of this, we're having to solve for that unit of time. We know that the amount after some period of growth is 18.7. So we have 18.7 equals 15.7 e to the 0.0416 t. And this is what we're solving for. So we're solving for a variable in the exponential level. And solving for a variable in an exponential level always comes down to isolating, okay, isolate the power, isolate the exponential term. So we need to get this exponential package, this entire term right here, all by itself, right? Because if we do that, then we can take a logarithm and kick this whole exponent down in front, right? So to get this by itself, we'd have to get rid of this 15.7. So you have to begin to see this power as one term, right? It represents one number overall, and that number is being multiplied by 15.7. So the first thing we're going to do is divide by 15.7. All right. Then we have our exponential term isolated. So 18.7 divided by 15.7. Got that right here. Okay, so we'll call that 1.19. I'm going to write 1.19 so I don't have to write it all out. Now, how do we get at this t, right? We get at that by taking the natural log of both sides, because in taking the natural log, the exponent will come down in front. So now I'm going to write this as the natural log of 1.19. is equal to 0.0416 t times the natural log of e, right? I very strategically chose the natural log and not common log and not log base 7. The reason we do natural log is because the natural log of e is 1. So that term, that part of this side disappears. And then all we have to do is divide by this coefficient of t to get our final answer. And again, this has been mentioned in a couple of previous videos. Just remember that I'm not dividing 1.19 times by this number. I'm dividing the natural log of that by this number. Okay, so if I go to Desmos, I'm going to cheat a little bit. Oops. There it is. And if I take this whole thing and I divide it by 0.416, I get 0.42. That doesn't make sense. Oh, found it. There we go. Right? Because we're talking about time in years, right? So this is approximately 4.2 years, right? So t is approximately 4.2 years after. So sometime in the middle of 2004 would be when that population reaches 18.7 million.